Hi guys, welcome back to the channel. In this video, I will be looking at aromatic chemistry from the A-level chemistry curriculum. So let's begin. So you are required to know of the structure and bonding in benzene. So first you need to know that benzene is aromatic. So this just means it has a ring. So looking at this as the benzene, so as you can see, this has a ring in the middle of it. So this is different to, for example, aliphatic. So in this case, looking at butane, this does not have a ring. And in benzene, each carbon is covalently bonded to two other carbons and one hydrogen atom. So as you can see in this case, we have one carbon, and this will be bonded to two other carbons as well as one hydrogen atom. So if you remember that carbon is able to bond to 4 atoms, in this case this is only bonded to 3. So what then happens is one of these electrons, so the fourth electron of carbon, is delocalized. And so benzene, what happens is in benzene, all 6 carbons, there will be an electron which will be delocalized, and all of these delocalized electrons, so 6 of them, form this benzene ring in the middle. So why does it form that ring? So if we were to say that this is how benzene looks like with a series of double and single bonds, what happens is that one of the electrons from the p orbital will become delocalized, and that delocalized electron does not stay in one place, so it moves around. So it will go from the double bond to the single bond, and that will form the double bond in a different place, and this will keep happening. So the double bond will keep switching around, and instead of having these arrows, we can just represent this by having this ring to represent our delocalized electrons, and this is a more accurate representation. That's why we use a ring. Okay, so you just need to be aware that those delocalized electrons makes benzene more stable. So this is because these electrons are not fixed in positions, so they are less available for a reaction. So compared to for example, an alkene, where we have the electrons fixed in that in that area, in benzene they are moving around constantly, so they are not in fixed position, and this just means that it's less available for a reaction. Right, so now looking at naming some aromatic compounds. So I have a few aromatic compounds here, and the naming process is pretty simple. You just need to learn a few examples, and then you'd be able to do the rest, really. So in that first case, so as I can see, I have a methyl here, and I have a benzene attached to it. So in this case, my methyl would act as a branch, so I can just call this methyl benzene. Same in the second example, so I have 2 methyl in this example, so I can just label this one carbon 1, this one carbon 2, and so I can say that this is 1,2-dimethyl benzene. With the third one, it would be the same, 1, 2, 3, so that would just be 1,3-dimethyl benzene. And for the fourth one, so I have 1, 2, 3, 4, so the second methyl group is on the fourth atom, so I can just say that this would be 1,4-dimethyl benzene. Okay, so now looking at chlorine, so it's the same as before, so it would just be chlorobenzene, and with a NO2 group. So we'll go through an example later on, but with an NO2 we just call it a nitro, so this would just form a nitrobenzene. And with a carboxylic acid, so instead of having that benzene at the end, it'll just be at the start. It'll just be benzene carboxylic acid. In that example, so the carboxylic acid is in the first and the fourth carbon, so we'll just call this benzene 1,4-dicarboxylic acid. So the next few examples are slightly different in a way. So in the first few examples, the benzene was the main ring, and the other, so the methyl or the other groups were branches coming out of it. But in this case, the benzene is the branch. So in that case, so for example, in the first example, so we have the alcohol here. So we'll say that this is our main bit and that benzene is a branch, so we would call it phenol. This is almost like methanol or ethanol. In the second example, we have an NH2, so this is an amine. So again, in that case, the benzene would act as a branch. So in that case, instead of having a phenamine, we call it phenylamine. So then looking at the third example, so what I can see is the second carbon. And so I can say that my first carbon's there, the second one's there, and the third one is there. So my second carbon is attached to a double bond O. So because the double bond O is in the middle of the chain, so that would be a ketone. So in that case, I'll call it phenylethanone. So on for a ketone at the end. So now looking at my final example, so what I can see is I have a C double bond O, and that C is also attached to a N. So I would be thinking that this would be an amide. And so in a normal amide, I would have C double bond O and then NH2. But in this case, that H, I only have one H, and the other bond from an N is attached to a benzene. So in that case, what I would be calling it is N-phenylethanamide. So that's just an example of an N-substituted amide. Okay, so now looking at Kekule structure. So Kekule proposed a benzene structure with alternate single and double bonds. So what he said is this is benzene, and what happens is, so 1 minute the double bond, for example, is structured like this, and the other minute it might change, so it might move to there, and this might move to there, and this one will move to there, so it will look like this. So this was his structure. And sometimes you can be asked to give the IUPAC name of this structure, so that would just be cyclohexa 135 triene. So if we were to say that this is carbon 1, 2, 3, 4, 5, so we take the shortest possible, the smallest possible numbers. So the first double bond is at 1, the second double bond is at 3, and the last one is at 5. So that would just be cyclo, because that's a cyclic compound, hexa, because there are 6 carbons, so 1, 3, 5, and triene because there's 3 double bonds. So we don't accept that structure, and we'll be looking at 3 reasons why we don't accept Kekule structure. So first, the reaction with bromine water. So if you remember, when an alkene reacts with bromine water, it will turn from an orange color to a colorless solution. So alkene just decolorizes bromine water. But when they did that with benzene, benzene did not decolorize bromine water, so it stayed orange, and that's why we can say that it does not have a carbon-to-carbon double bond. Secondly, looking at the bond length, so the bond length of a carbon-to-carbon single bond is longer than the bond length of a carbon-to-carbon double bond, as you can see in this example. So what this would mean is a structure of cyclohexa 135 triene would look something like this. So as you can see, the double bonds are smaller than the single bonds. However, when we saw the structure of benzene, what we saw is the benzene has a perfect hexagon shape, and so it does not have. So this just indicates that it does not have any alternating double and single bonds, and all of the lengths of benzene were around 0.140. So this does not go with the Kekule structure. And finally, the enthalpy of hydrogenation. So this is just adding hydrogen to that's a cyclohexa 135 triene to make it saturated. So if we have one double bond and we add hydrogen to this and to make it saturated, so saturated just means that there can be no further bonds formed. So in this case, this is not saturated because we can still add hydrogen bonds to this, but this will be saturated. So the enthalpy of hydrogenation of this structure was minus 120 kilojoules per moles. So in that case, this would mean if we had 3 double bonds for the structure of benzene, then surely the enthalpy change would be minus 360, just timesing minus 120 by 3. But when they did that, they got a different value. So they got minus 208 instead of getting minus 360 for the enthalpy of hydrogenation of benzene. This just indicates that benzene is more stable than Kekule structure. And as we know, that this is because the electrons are in that ring, and this makes them less available, and they're more stable, so they are less likely to react, and that's why the enthalpy change is lower than what Kekule would have predicted. Alright, so looking at electrophilic substitution in benzene. So benzene is very stable, so that just means that it will only react with the strong electrophiles. So if we remember with alkenes, if we had Br, and so just bromine, so what would happen is as the bromine comes close to that double bond O, this can cause the partial charges to build up. So that becomes a partial positive charge, and that would become a partial negative charge. So then what would happen is that double bond would attract the bromine, as that has a partial positive charge. But in the case of benzene, the bromine cannot react because the benzene is very stable, and that's why it will only react with the strong electrophiles. So we can't react with Br delta positive charge. So if it was Br just plus, then the benzene might be able to react with that. So that's why we want these strong electrophiles. So now just looking at the mechanism of how it reacts. So I'm just going to call my electrophile E plus, and the plus is really important in this. So if I'm drawing my benzene, so I've got this hexagon and with a ring in the middle. So my first step would be a curly arrow coming from the ring towards the strong electrophile I have, and this would just form a bond with that electrophile. So now drawing my benzene again. So this will look the ring would look slightly different now. So that curly arrow has used up 2 of my delocalized electrons. So when I'm drawing my benzene now, I would have to take that into account. So this is a carbon and this is a carbon. So I'm just going to say that the delocalized electrons that have been used up were from this carbon. So now when I'm drawing my benzene ring, it would look slightly different. It wouldn't really be a ring. So I would start from here, so in line with this carbon, and I would draw up to the carbon, my last carbon, so my 4th carbon, and I would leave the bit out which involves both of this. So this bit would not have a ring because I've used the delocalized electrons from this side, and because we bonded to a positive electrophile, we've got a plus in the middle. So for the next step, I'm just going to draw a bond from the carbon going to a hydrogen. Just remember that we do have a hydrogen bonded to all of these. So what I'm going to do now, I want to get my ring back, so I'm just going to take the electrons from that bond. So these 2 electrons will go from that bond, and a curly arrow would be drawn from that bond to that plus charge. So what that means is that we've just taken those 2 electrons, and they would now form our delocalized electrons. So finally, if I'm drawing the benzene structure now, so I will have a full benzene ring now with the E there, and that's also formed a H plus because we have removed the bond now. So that would be our electrophilic substitution. So now looking at nitration. So in nitration we just form a nitrobenzene. So the reagents in this case are H2SO4, concentrated H2SO4 and concentrated HNO3. and the H2SO4 will act as a catalyst. And what our electrophile in this case would be NO2+. So you're starting with H2SO4 and HNO3. So I've got these two reactants, if you like, and then we have the arrow. And so I know that I'm going to be forming NO2+ with that because that's my electrophile. So I will have that NO2+ here, and the next two products that I have, you just need to learn them. It's very difficult to derive them from the equation, so I'm just gonna I just know these. So it'll be H3O+, and it's also HSO4-, and to at the end, to make sure that they're balanced, what I do is I add a 2 in front of the H2SO4, and I add a 2 in front of the 2HSO4-. Right, so now looking at the mechanism for nitration. So again, I'm going to draw that benzene ring, and I'm going to have my electrophile NO2+. So now my curly arrow would be coming from inside that ring, so from that ring, and that's going to attract my NO2. So now next, I'm going to form that bond with the NO2, and that there will be also a bond with the H, and you just need to show that now. So now when I'm drawing my ring, it won't be a full ring, remember. So it would be from it would be cutting out that carbon and the other carbon. So that's my new ring, and there will be a plus in the middle because now we have bonded to that NO2. So finally, what happens is that bond between the C and the H, we just show a curly arrow from there into that plus, because we'll be breaking that bond, and the electrons from that bond will be becoming the delocalized electron inside that ring. So finally, when I draw this now, I will just have a full ring inside that, and I will have a bond to NO2, and I will also have that H+ there now. So you can be asked what the product is. So this has formed a nitrobenzene, and also you can be asked about the equation of the whole reaction. So remember that we don't include the catalyst in our overall equation. So we have benzene at the start, and then we have the HNO3. So we have formed that nitrobenzene, and we would also have formed a H2O. So you can just include that. And also why H2SO4 is a catalyst. So if you see now, we have that H+ there. So now that H+ can react with the HSO4-, and that would form H2SO4. So that's why it's a catalyst. Okay, so now looking at Friedel-Crafts acylation. So in this case, my reagents, it would be alkyl chloride. So in this case, I've just got ethanol chloride, and my catalyst will be aluminium chloride in this case. And my electrophile in this case is an isalium ion, so CH3 C+O. So how do I get my electrophile in that case? So what I would do is I would react the reagents together. So CH3 COCl, and the catalyst AlCl3. So what this forms is AlCl4-. So that Cl from that ethanol chloride is given to the AlCl3, and that would end up forming CH3 and C+O. So that's my electrophile. And just remember that C is next to the carbon. Don't put it next to the oxygen, because you will end up losing the mark. So that's how I'm getting my CH3 C+O electrophile. Now on to the mechanism of this. So again, I'm just going to draw a benzene, and that ring in the middle. So I have my electrophile as CH3 C+O. So what I do now is I would just have a curly arrow going from the ring to my electrophile. So then that would form a bond with the electrophile, and remember that my ring will no longer be a full circular ring, rather it would be now in a horseshoe shape, and I would have a plus in the middle, and now it's bonded. So remember, because we bond to that C plus, so this would look like COCH3, and I would also have a H there. So finally, what happens is that bond between that C and the H breaks, and we would end up getting the delocalized electrons back into the ring. So we have a full ring now in the middle. So that ring's formed. We end up getting COCH3, and we also have a H plus there. Okay, so you can be asked about the product you formed with this. So the product in this case is my phenyl ethanone, and my product would always be a phenyl ketone. And you can also be asked about the overall equation. So the benzene plus the ethanol chloride. Remember, we don't include the catalyst, and so we end up forming our phenyl ethanone as well as an HCl in this case. So sometimes they also ask you about Friedel-Crafts acylation with a acid anhydride. So in that case, you'd still be forming a phenyl ketone, and you just have a acid anhydride at the start, and the benzene the same as before. So you form that same product, but it's just at the end you would be forming a carboxylic acid, so the original carboxylic acid, and that's the only difference in this. Okay, so now looking at the reduction of nitrobenzene. So reduction, what it does, it basically converts the nitrobenzene into phenylamine. So looking at this, so this is our nitrobenzene. So it just converts that into phenylamine. So instead of having that NO2, we just have that NH2 now. So how does it do it? So the reagents are HCl, and we have a tin catalyst, so the SN as the symbol for it. And the conditions are high temperature as well as high pressure. That's all you need to know about the reduction of nitrobenzene. You don't really need to know a mechanism for this. So finally, looking at the derivatives of aromatic compounds. So nitrobenzene derivatives are used as explosives, so they're useful as they can be used in explosives. So make sure that you mention nitrobenzene derivatives. Don't just say nitrobenzene can be used as explosive. So many people say that and they lose a mark. So make sure you say that nitrobenzene derivatives. So just remember, derivatives are used as explosives. So for an example is this aromatic compound, which is called 2-methyl-1,3,5 trinitrobenzene, and this is known as TNT, which I'm sure some of you would have heard of. And we can also have phenylamine derivatives, which can be used to make dyes such as azo dyes. But the main one is nitrobenzene derivatives, which are used as explosive. So just remember that. Thank you so much for watching this video. If you did like this video, don't forget to subscribe to see more of these, and you can watch my recent videos by clicking on the links popping up. Thank you.